I'm a technical leader at Nomadic Labs, and this is Andrea Cerone, which is a technical leader for TreeTech. And we will present you data availability solutions for Tezos. So the few talks before, so Arthur, Thomas, and Hema advertised a bit what are the solutions. So the data availability committee and the DAO. The solutions are built upon our smart rollups product. Arthur already advertised a bit this idea of moving the execution layer into the L2 thanks to the smart rollups, so that the L1 can focus on high decentralization tasks, such as the consensus or the data availability, for example, that we will present. The way the smart rollups takes its transactions at the moment is made mostly thanks to what we call the shared inbox that we will present, and using data availability solution, either the DAC or the DAL. The good thing with smart rollups is that they are enshrined, and this enables, for example, the UHT use case, but many other ones. They are permissionless, and they can be programmable, thanks to what we call a kernel, for example, which contains the core logic of the smart rollups. So this is a rough picture, and here I've pictured Tezos network, so it's a schematic version of the network. There's not 5 nodes in practice, but many more. And what I wanted to picture here is that if you have a block, for example, that goes through the network, every node needs to download all the data, right? And so as a rollup, if they want to read their transactions or instructions for the rollup, they read it directly from the block. And inside the block, thanks to the smart rollups, there's something called the shared inbox, and they just read their transactions from it. The problem is that if we only use this shared inbox, we are limited in terms of throughput, and roughly more than 3,000 of transactions. But just before, you have seen the demo that shows that we can reach 1 million of TPS with smart rollups. And to do so, we need to leverage the limitation of the bandwidth. So either we relax the size of a block, that we don't want to do, because we want, as Arthur mentioned, low requirement machines on the L1. And so the other way to do that, if we want to reach 1 million of TPS, is to put the data of the rollups outside of the layer 1. And so basically now, for your rollups, you have 2 ways to read instructions, either from the node with the shared inbox, or directly fetch and read the instructions from an external storage. And now, this is what we call the rollup booster. And so we have 2 solutions now as an external storage. But just before, I will sum up the problem by doing that, because it's not that easy. First, now your rollup, how he can identify the data he wants to fetch. How do you say, I want those data? Then, because it's permissionless, anybody could track the rollup, and so could fetch some data to the rollup kernel logic. But are there the correct data? Are those data the ones you want, or just other data, malicious ones? So we need to ensure the integrity of the data that are imported inside the rollup. The third problem, which is actually the main problem behind the data availability layer solution, is how do you ensure the existence of the data? So Arthur mentioned earlier that data availability is actually a bad name. And the reason, he says a better name would be a proof of not existence, proof of existence of publication, sorry. So the term was proof of publication. And the idea is really to prove that those data exist somehow. And finally, you need your solutions to make the data accessible to your rollup. So an easy idea, let's say a simple idea, is to use a committee. So you have an infrastructure which is could be deployed by a single rollup, where you have maybe a multi-sig or something like that. And this way, you can have privacy so that you don't have to share your data with everyone, and also you have an unlimited bandwidth, because now you can just use your DAC and fetch the data to the rollup. The more complex solution we want to push, for example, for the UHT project, is the data availability layer. And the main complex part here is to have another P2P protocol where the data can go through. And now your problem is to ensure that the data actually went through this layer. And to do so, we reuse the consensus of the L1. So we could, there are other companies such as Celestia that also develop a DAL. And one purpose of reusing the consensus of the L1 is for security reasons. It gives a better security model, as advertised by Arthur earlier. And so now I leave the floor to Andrea for...
Okay, hi. So yes, I'm going to talk about data availability committees. So basically, what is a DAC? You have seen it in action for the demo already. The idea is that you have data that you want to make available to smart rollups, but you don't send this data to the blockchain, to the layer one directly. Instead, you send it to a set of entities, multiple entities called the Data Availability Committee. They will just store this data offline, and they will provide it to smart rollups when necessary. And as Arthur mentioned before, like, you don't need necessarily all the Data Availability Committee members to be honest to provide the data. You just need one to make the data accessible from the rollup. Now, let me show how it works without data availability solutions to inject a message into a smart rollup. We have the message, and the idea is that we send it directly to the layer one. It will include it in a block in the rollup inbox. And the rollup node, which is responsible to run the rollup program, the rollup kernel, will download this block, and it will eventually import it for it to be processed. Now, with data availability committees, the situation looks much more complicated, but let me explain. Like, we have now a payload that can be, for example, for the demo, it was 2 megabytes in size, more than a block. And this payload is actually sent to a DAC infrastructure, where the data availability committee members will download the data, and they will sign a proof of availability, and they will return a certificate that it's quite small in size, and this can now be sent through the global rollup inbox for the rollup node to eventually download the block and give the certificate to the rollup kernel. The rollup kernel will validate the certificate and say, oh, there is some data from the data availability committee that I can download. And it will request the rollup node to actually download the data, and it will start processing it. Now, we have released technical documentation to get started with DAC. You will need to build your own infrastructure for running a DAC, and you can experiment with it. Or we actually are setting up a community DAC that I have to mention is not ready for production use, but you can start experimenting with that. This link, if you try to use it on Chrome, it won't work because it's just the endpoint to send payloads to the community DAC. And also, there is an example that will be merged in the kernel gallery soon. Like, it's currently in review. We need to make some changes, but it works for actually seeing how you can use, you can code smart rollups that uses the community DAC. And actually, we are going to see how it works in action. Okay, on the left screen, I am going to run a rollup node for a smart rollup on a RobbieNet. So this rollup already exists on a RobbieNet, and we'll just start it. On the right hand, oh, by the way, what this rollup does, the kernel will just download data from the data availability committee, and it will display it on its log. On the top right-hand side, I'm going to run the DAC node, which is responsible for bridging the community DAC with the rollup node. And here on the bottom right screen, I'm going to launch the commands that I will use to send the payload to the data availability committee and to send the certificate that I get back to the rollup. So the payload that I've chosen is just a fairly small file of 5 kilobytes. It's the canto primo of Divina Commedia. The idea is that I'm going to send with the DAC node, with the DAC client, the payload to the DAC and wait for at least 2 committee members to sign and give me back a certificate. Okay, was passed. We get the certificate back. And now the last command is that I take this certificate and inject it as a message to the global rollup inbox on a RobiNet. So if everything works well, the rollup node will pick up this certificate, will download the original payload from the DAC, and will display it on screen. And there you go. So. And that's the DAC in action. Thank you very much.
So, for the data availability layer, I will start with an overview. And the bad news here is that it's fairly complex. But fortunately, the good news is I will try to simplify this workflow for you. The first thing you should notice is that the same way there is a DAC node, there will be a DAL node. So maybe it will be a bit more complex for the users, but it's a way to ensure modularity between our infrastructures. And the way we will build the data availability layer is made so that only the DAL node knows how to interact with it. So anytime you want to interact with this new P2P protocol, you will use the DAL node. So let's take the point of view from an operations and how a user that wants to submit operations onto the DAL can actually use them from the rollup point of view. So it's permissionless. So actually anybody can submit data onto the DAL. You don't need to be a rollup operator. You just need to say, I want to submit data onto the DAL. So let's say someone does that. You use a DAL node. The first thing you need to do, and I will explain a bit later, is that we need to post a commitment. As I mentioned earlier, we need to ensure integrity of the data. And the commitment is the way that we ensure the integrity of the data posted onto the DAL node. So the new L1 blocks of the chains now contain a port where they store the commitments. The point of having a commitment is it's very small. It's like 50 bytes, right? So you have this commitment at some level, here 100, and then the DAL node will send what we call shards onto the data availability layer. Why are we sending shards and not the entire data? It's because we need to split the data into very small chunks so that the ones that do the consensus of the L1, so the bakers, only need to fetch a small part of those data. So when the shards are sent onto the layer, you have the role of the new role now of the bakers and the attestors is to connect onto the data availability layer with the DAL node and to check whether the data are actually there. So they are assigned to some shards and check whether the shards are there. So you need sometimes to do that, and then at some point, at the moment roughly around 1 minute, the bakers can say in their attestation, so formerly known as endorsement, whether the data were there or not. Once it's done, if the rollup wants to use the data, what it has to do is to connect to a DAL node and ask the DAL node to fetch the corresponding data as shards. Those data will be reconstructed and the rollup can use them. Now I would like to focus a bit more about how the DAL from the L1 is structured. And I think it's important because it's, as Arthur mentioned, we have Ethereum that is doing data availability layer known as chunk sharding. We have Celestia, and there is something very specific to Tezos here. What is specific is that the way we post the data onto the DAL, so of chains, are organized into slots, roughly about 1 megabyte. And the point of doing that is that as a rollup, you are free to choose your slot. And so you don't need to use a third party to use the DAL, right? Any rollup can choose to use the DAL directly without relying on a third party. On Ethereum, for example, their current design is to use only one slot. So if you have multiple rollups that wants to use the DAL, somehow they need to connect if you want to avoid friction. Our target bandwidth at the moment is to reach a bandwidth for the DAL of around 10 megabytes. The other technical detail here is that actually a slot you need some structure for the slot. So I won't describe what is a page, it's related to a technical detail for the smart rollups. But what is important is that actually what we put into the data availability layer is not the data themselves. What we do first is to compute an erasure code so that there is some redundancy into your data. The reason for that is because we want to reach a consensus. We cannot expect all the bakers to be connected at the same time, and so we only need part of the shards to reconstruct the original data. This way, if some baker is offline, it's okay. You still need sufficient amount of bakers to attest the availability of the data. So you compute your erasure code, and then you split it into chunks that we call shards. And from that, there are two things we can do. We can compute a commitment that will be posted onto the L1. But the very nice properties that we get from the cryptography is that it is possible to check the integrity directly from the shards, whether it's correct, whether it's part actually from the original slot. And this is necessary if you want to prevent a DDoS attack. So, the other important point in Tezos for the interaction with the DAL is that it's up to the smart rollup to decide the data he wants to import. So with the shard inbox, the logic is made so that all the data from the shard inbox needs to be imported from the smart rollups. But with the DAL and with the DAC, actually, it's up to the kernel logic to decide how the data will be imported. So for example, the rollup can say, I only want the data from the slot 0, or something like that. So it will work in 4 steps. First, the smart rollup requests some data. So it needs to identify the data. The DAL node will fetch the data onto the data availability layer. Then you need to reconstruct the data because what you get are shards, and so from the shards you need to reconstruct the original piece of data. And then you can provide it to the smart rollup. The last piece to understand how the DAL works is to understand the consensus part of this scheme. So what we call an attester here, it could be a baker. And so now they have this new role with the data availability layer, which is to get the data from the DAL and attest whether or not they are there. So to do so, the attester will read the commitments from the L1 blocks. And if there are commitments, now they need to fetch the corresponding shards into the data availability layer. And what we can expect is that the more share you have, so the more stakes you have, the more shards you need to download. So that if you are a very small baker with only a few roles, you won't need a big bandwidth to download those shards. So once the attester gets some shards, it can put the result of what it downloaded into what we call attestations and publish that into the L1. And from that, the L1 gathers all those attestations and says if there are enough attestations for the data is available and it can be used by a smart rollups. So in terms of security, at the moment, with what I've showed you, we rely on a majority of honest bakers. What it means is that we need maybe between 30 to 60% of bakers to be honest. So the current state of the art, if we want to leverage this limitation, is to use a method what we call sampling. So what we plan to do at the moment is to release first a DAL in version 1 without the sampling, and in the future version to release it with sampling. What we call by sampling is the idea that not only we will request the bakers to download data from the DAL, but actually all the L1 nodes. So even the ones that are just validating blocks. And you propagate your blocks now. So any nodes will propagate the blocks if they manage to download the corresponding data onto the DAL. So they sample shards, and if the sampling is successful, they propagate the block. At the end, something that I will not describe, I know it was already a bit technical, right? But if we talk about the P2P protocol, it's even more technical. But what I can say that we re-implemented a known algorithm for the DAL, which is called gossip sub. Gossip sub is an algorithm that is already used by Ethereum and other many famous blockchains. And what it gives us is the way to split the bandwidth for any actors. So if you are a small baker, for example, and you connect onto the DAL, you won't receive all the shards from the network, but only the ones you want. So at the moment, we don't have a demo, and maybe next year, the point of it's to run the same demo with the DAL. But what can conclude? Mainly, the way we identify the data with the DAC and the DAL is a bit different. With the DAC, we have a certificate, while with the DAL, the kernel will have to identify the data with a level and a slot index. To check the integrity, for the DAC, we reuse a hash function. And for the DAL, we use something a bit more involved, relying on cryptography, which is called a commitment. So the main issue to ensure the existence of the data with the DAC is to trust the DAC members, while for the DAL, we reuse the L1 consensus. And later on, we will use also the sampling. And finally, if we want to make the data accessible, with the DAC, we reuse the DAC infrastructure, while for the DAL, it's permissionless. So anybody can connect to the DAL by running a DAL node. So here is quickly a summary to know whether you would like to use the DAC or the DAL. So with the DAC, you get privacy and unlimited bandwidth, while with the DAL, you get a decentralized solution, which is also plug and play. So the advantage is that instead of running your own DAC, you just need to run a DAL node and put the data there. The cons for the DAC is that the DAC is a bit more centralized, even though it can be controlled by a multisig. And the users need to deploy an infrastructure. While for the DAL, at the moment, we have a limited bandwidth, but should be high enough for many use cases. But we don't have also a built-in privacy. So what's next? At the moment, the DAC is already released. It's available for Nairobi. We have the DAL on test networks, such as Mainnet, and we plan a release for Mainnet in 2024. And if you are curious about those two solutions, those are QR codes to blog articles we released to go into a bit more details. Thank you.
So, last thing that I would like to add is that between DAL and DAC, several engineers from Functory, Nomadic Labs, Trilitech, and Marigold work very hard, and they did an excellent job. Thank you very much to them.
Are there any questions? Or sure.
Is it going to be possible to make sure that the data is actually stored in data availability layer from smart contract on layer 1?
At the moment, there is no compatibility for the DAL with smart contracts, right? So we plan an integration of the DAL with smart rollups. And if people writing smart contracts want to integrate the DAL, this is something we could consider.
Yeah, I mean, typical use cases when you wanted to settle in not like smart rollup, like some alternative rollup, right? And on the settlement layer, you want to make sure that the data is actually was pushed to the DAL. So
so that could be doable, but you would get the same guarantees than the one you have for the smart rollups, meaning that you will get a proof of publication, but you won't get a proof of storage. Yeah. So if you want a proof of storage, you need something else. So people talk about having retrievability solutions. Like once your data is published, you want to be sure that you can get your data, I don't know, maybe 2 weeks later or 1 month later. And at the moment, people are saying that this problem is easy. What is hard is publication. So once you know it's public, then you get retrievability thanks to kind of social ways, because you expect that people will run archive nodes or stuff like that that will archive the data. So you don't get that directly from the DAL protocol itself. You get that more because you expect indexers or stuff like that to do that. So I guess depending on your use case, if you want retrievability, you need to have a kind of ad hoc solutions, so you can use the DAL itself, but it's just you cannot expect that the DAL will provide you a proof that the data are there forever.
Okay, I see. Thanks.
All right, can we get another round of applause for these guys? All right.